Okay, so today we're going to continue with our theme of forces and talk about two really important forces that affect our everyday lives that are super prevalent and super important in the universe, super relevant to the functioning of the universe that can help us explain and understand why certain parts of the universe do what they do. So we're still using Newton's laws of motion, his forces. Remember, law one says that an object at rest wants to stay at rest, an object in motion wants to stay in motion. An object will not change its motion, it will not accelerate unless there is an outside force acting on that object. Law two, if you remember, we can explain with an equation. The sum of all the forces acting on the object is equal to the mass of the object times the object's acceleration. And so the net force on an object is directly proportional to the resulting acceleration. The resulting acceleration is inversely proportional to the mass of the object. That's Newton's second law. And then hopefully you guys remember the third law. The third law is going to be really important to keep in mind during our discussion today. The third law says that if you have two objects interacting with each other through forces, so object A, object B, and object B is exerting a force this way to object A, so I can say the force felt by A dealt by B. There's always going to be another force acting on the other object, the force felt by B dealt by A. Maybe B is you pushing on a wall. Object A would be the wall, so the wall is feeling your push. What does the wall do back? The wall pushes back, so you feel the wall's push. Remember, Newton's third law says that those forces are equal in size, but opposite in direction. So that's going to be really important today to remember as we talk about these two fundamental laws of the universe and the way the universe works. The first one is about gravity, Newton's law of universal gravitation. Newton was the first one to figure this out and really formalize this in a law and a mathematical equation, as we will see. Now, you know some of this already if you watched the quick note about gravity before. You should know this statement. Gravity is an attractive force, so it's a force of attraction. Things attract each other between objects which have mass. So we're talking every single object in the universe that has mass. They're attracted to each other gravitationally. Technically speaking, I am gravitationally attracted to the laptop sitting in front of me. The laptop sitting in front of me is gravitationally attracted to me. The thing about gravity to keep in mind, though, is that it's incredibly, incredibly weak. The force due to gravity is really tiny. It takes a huge mass. It takes a lot of mass to have any true effects at all. Think about it. We're all on the surface of the Earth. The Earth has an enormous mass, which we will actually be able to calculate later. The Earth has an enormous mass, and we can feel its effects. We can feel the gravitational effects of the Earth. So it takes an enormous mass to really have an effect because gravity is so weak. So let's say that you are setting up an experiment, and here's some data that you've collected. You're trying to figure out the size of the force of gravity and what affects it. So the force of gravity may be your dependent variable. What does it depend upon? How is it related to other variables? Well, we know from the definition that gravity is an attractive force between masses, and that the object's mass plays a role. So maybe you're going to take the mass of two objects, the mass of object 1, the mass of object 2, and those are some independent variables that you're testing. And then maybe you think, okay, so probably the force of gravity will be affected by how massive the objects are. But is the force of gravity also going to be affected by the distance between those objects? That kind of makes sense, right? Gravity is a force that can act over a distance. If you throw a ball up in the air, it will still be pulled down by the Earth's gravity even though it's not touching the Earth. So gravity is what we refer to as a field force, which means that it acts over a distance. There is a gravitational field that kind of radiates out from all massive objects. It's a field force that acts over a distance. So maybe the distance matters, how far apart the objects are. So this is the data you're taking. I kept it really simple. And I want to see if we can find a pattern, find a relationship, and maybe if we ourselves can derive Newton's law before we actually look at it. So you can see here, if we have a mass of 1 kilogram 1 meter away from another massive object of 1 kilogram, So that would be like maybe some spheres. Here's a sphere that has a mass of 1 kilogram. Here's a sphere that has a mass of 1 kilogram. The distance between them would be 1 meter. And I want to know what gravitational attractive force do they feel. Now remember, there's really two forces here. If this object is pulling on this object gravitationally, then by Newton's third law, this object has to be pulling on this object gravitationally. So two forces. And I'm just measuring the size of one of these forces. That's all I'm measuring. And so let's say I'm able to measure that. I have a force sensor or something. You remember we said that gravity is really weak. So here's how weak this is, and this is an actual result that you would get. 6.67 times 10 to the negative 11th. That would be 0.0000000000667. That's incredibly tiny. It's measured in newtons. This is actually a really important number that we will talk about later. It's called big G. Don't get this confused with little g that we talked about last unit. Hopefully you remember what little g is. Little g is the acceleration due to the force of the Earth's gravity near the Earth's surface, 9.8 meters per second squared. That's little g. This number here is a big G, which we will talk about later. So it turns out that if you're doing this experiment in the first row, 1 kilogram objects 1 meter apart, this is the force of gravity that's going to be between them. So let's first test the mass of the object. So if we double the mass of object 2 over here, it's now 2 kilograms. So we make it larger, 2 kilograms. We keep them the same distance apart. Mass of object 1 is still 1 kilogram. What's going to happen to the force of gravity? We doubled the mass. If you compare these numbers mathematically, what happened? That is a doubling. That also got doubled 2 times. That's interesting. So maybe we should be thinking that the force of gravity, if the mass doubled and then the force of gravity doubled, maybe we should be thinking that the force of gravity is directly proportional to the mass of the objects involved. Double the mass, double the force. That's interesting. What happens if we now double both of the masses? So we double the mass of object 1. We double the mass of object 2. What happens to the force of gravity from here to here? 1 kilogram, 1 kilogram, 1 meter apart, this was the force of gravity. But now if we double both of the masses, what's going to happen? Do you see the pattern? It's now quadrupled. This is a 4 times relationship. So that makes sense with our last results. If we double the mass of an object, the force of gravity doubles. If we double the mass of both objects, the force of gravity quadrupled. So I think we have just shown that the force due to gravity is proportional to, remember, this little symbol here means proportional to, I can never draw it perfectly, is proportional to the masses of both objects, maybe the mass of object 1 and the mass of object 2. If we double one of these, the force is going to double. If we double the other one, the force is going to double. If we double both of them, 2 times 2, the force is going to quadruple. That's exactly what we've shown. So interesting. We're kind of working our way to finding a mathematical model of the force due to gravity just by looking at some data. What about the distance, though? So if we keep the masses the same, 1 to 1, 1 to 1, but this time we double the distance, so the distance has been doubled, what happened to the force of gravity? Well, this time the force of gravity got weaker. Do you see that? It went from 6.67 times 10 to the negative 11th to 1.67 times 10 to the negative 11th. If you get out your calculator and find the ratio there, you will see that that just got cut by a factor of 4, 1/4. So that's interesting. Wait a second. We didn't increase the distance by 4, we increased it only by 2. We doubled it. And yet we cut the force of gravity by 1/4. So that's interesting. Let's try another experiment. What happens if instead of doubling, we triple the distance between them? So now they're no longer 1 meter apart, they are 3 meters apart. What's going to happen to the gravitational force then? So let's compare these numbers. I'm going to give you a second to see if you can figure out the relationship. So if we triple the distance, the force of gravity ends up getting cut by a factor of 9. This is 9 times smaller. 6.67 times 10 to the negative 11th divided by 9 would give us this. So do you guys see a pattern here? The force of gravity is inversely proportional. Why am I saying it's an inverse proportionality? Because as the distance goes up, the force of gravity went down. It's an inverse proportionality between the distance squared. Do you guys see that? You double this, and the force of gravity gets cut by 4. 2 squared is 4. You triple the distance, the force of gravity gets cut by a factor of 9. 3 squared is 9. So we have this proportionality. The force of gravity is inversely proportional to the square of the distance between the objects. So we can put all of this together now to get actually Newton's law of universal gravitation. And here it is. I've just put it in words. The gravitational force between two objects is directly proportional to the mass of the objects, the masses of the objects, and inversely proportional to the square of the distance between them. Force due to gravity is proportional to the masses of the objects, directly proportional to the masses of the objects. This doubles, the force doubles. This doubles, the force doubles. Both of them double, the force increases by 4. But inversely proportional to the square of the distance between them. I'm going to use the letter R now to represent distance, almost like radius, the distance between the objects. So if the distance is increased by a factor of 2, 2 squared is 4, 4 is on the bottom on the denominator, so the force will get cut by a factor of 4, by 1/4. If we triple the distance between the objects, 3 squared is 9, the force will get cut by a factor of 9. We'll have 1/9 of the force. So remember how we can turn a proportionality into an actual equation. We add what's called a proportionality constant, a value that remains constant. The proportionality constant that we use for this is called big G. That's that number that we saw earlier when the masses were 1 times 1 divided by 1 squared. So all of this is 1. The force of gravity was big G, that super tiny number. So we have just shown Newton's law of universal gravitation. You guys need to remember this, write this law down, and you need to understand what it means in words. The force of gravity is directly proportional to, here's our proportionality constant, directly proportional to the masses of the objects, but inversely proportional to the square of the distance between the objects. We call this an inverse square law. There are many phenomena in nature that end up being inverse square laws. We're going to see another one of them later today. But this makes sense because we have a square, something squared on the bottom. It's inversely proportional to the distance between the objects squared. So we call it an inverse square law. So here's all this kind of shown on the picture. Let's say that we have two massive objects and we take the distance between them. Notice we measure the distance from their center. We call that the center of gravity. So we measure the distance from the center. We're going to use R to represent that. Then the force felt by object 1. So this is a force of gravitational attraction felt by object 1. I'm going to complete their feeler-dealer. Felt by object 1, dealt by object 2. This is a force felt by object 2, dealt by object 1, gravitationally speaking. Remember, they have got to be equivalent because this is a third law pair. Mass 2 pulls on mass 1, mass 1 pulls on mass 2, and they're equal. And how can we calculate what one of those forces is? Well, here's what we said earlier. Big G, the proportionality constant, that's known as Newton's universal gravitational constant, the product of the masses over the distance between them. This is Newton's law of universal gravitation.